Chemistry. Today we are going to continue in our thermochemistry chapter. We introduced this idea of energy. So energy is exchanged between the system and the surroundings through work and heat. Work is technically a piece of this puzzle. It's a piece that's really hard for us to manage as chemists. So moving forward, we're actually going to just ignore this work piece for now, and we're just going to focus on heat. If we ignore that work piece, from here we can say that anytime we're monitoring the change in energy, that's the same thing as just monitoring the heat of a reaction. So heat is denoted with the letter Q. Don't ask me why, I have no idea, but it is. So heat is denoted with the letter Q. And from now on, heat and energy are going to be used synonymously. So heat is the transfer of thermal energy between two bodies at different temperatures. So for example, if I heat up a piece of metal really, really hot, I drop it into room temperature water, that metal is going to transfer its heat from the hot metal to the room temperature water. And it's going to continue to do that until the two are at the same temperature. So that's how heat is transferred. Heat flow, which is a kind of a redundant term, but heat flow is the transfer of thermal energy from one body to another body. So it's that movement of heat from the hot piece to the cold piece. Okay. Substances are placed in contact. The thermal energy always flows from high temperature to low temperature. Depicting this very thing. So we've got our two different samples at different temperatures. So the red indicates hot, the blue indicates cold. Here they're going to stay at those temperatures because they're not in contact with one another. The second that those two come into contact with one another, we're going to see this heat flow. It's going to go from the hot object to the cooler object, and that heat is going to continue to flow in that direction until both objects are the same temperature. And so this is just the facts about thermal energy, how that heat flows. Heat flow from whatever the surroundings are into our system. Let me first define our system. So as chemists, we are particularly interested in what's going on right in front of us, right? So we typically have a beaker or a test tube, something like that. And what's going on inside of that beaker or a test tube. So that's our system. The surroundings would be anything else. Typically, we think about our immediate surroundings, so the table, the room, anything that beaker is touching, but really the surroundings can be anything else. So if we want to consider or measure the heat transferred from a surroundings into our system, so heat can go into, be absorbed by, or it can be released. I'm going to talk about absorbed just so I'm not bouncing back and forth, but just know everything I'm about to say will work for heat being released as well. So if we want to monitor the heat that's being absorbed by our system, what are some things that we have to consider? So remember, heat is a measure of energy. So if I wanted to determine what the unit for this heat would be, well, what are our units for energy? Yeah, right? So that's going to be our unit in joules. That I have to consider when I'm trying to determine the amount of heat that's absorbed by our system. Well, certainly there's going to be some sort of change in temperature, right? So I can monitor the change in temperature of our system by sticking a thermometer in it. So that's certainly going to be something we consider. The other thing we need to consider is how much we have in our system. So another fact we're going to multiply this by, and that's going to be the mass. Okay. If I have a little tiny sample of metal or if I have a huge, ginormous chunk of metal, that's going to be a difference in how they absorb heat, right? So we have to consider how much we have. And then the last thing to consider is what we have. A piece of metal is going to absorb heat differently than a piece of wood, which is going to absorb heat differently than a piece of plastic, which is going to absorb heat differently than water, right? So whatever the substance is going to factor into this. So the way that we acknowledge the difference in substance is with this new variable C. And this C is called the specific capacity is going to tell us that metal will absorb heat very differently than water would absorb heat. And then iron will absorb heat different than aluminum absorbs heat. So that's just acknowledging what our substance is and how that substance will take on that heat. We call that specific heat capacity. Formula to determine the heat that's being absorbed by a system. That specific heat capacity really is the new term here. We've dealt with mass before. We've dealt with change in temperature. The specific heat capacity is the quantity of heat required to change a substance by 1 degree Celsius. Of specific heat capacity. So this is something that would be given to you in a problem. So let's take a look down here at some of our metals, yeah? So if we look at things like lead, copper, iron, we see that the specific heats of these guys are relatively low, okay? So something that has a low specific heat or a low heat capacity. What that means is I can expose those to a heat source and the capacity to take on heat, right? So I expose them to a heat source, and quickly there's going to be a big change in temperature, so a very large change in temperature, okay? Advantage, right? So if we think about what our pots and pans are made of, things like copper, iron, right? Iron skillet. So we use this to our advantage. We expose them to a small heat source, right? Whatever we're using on our stove. And what happens to that pan? Well, with that teeny tiny heat source, that pan heats up a lot, right? And we use that to cook our food. So having a low specific heat means we apply a heat source. It doesn't have the capacity to take on that heat, so boom, we see a big change in temperature. Like water, comparatively. Water has a very high specific heat, okay? So having a much higher specific heat capacity, we could expose water to that same heat source, and water has a large capacity to take on heat, right? So it's going to take on that heat, but we're not going to see a very big change in temperature. So it'll have a small change in temperature, okay? Advantageous for us. So our bodies are made up of like 70 to 80% water, right? So let's say we wanted to go, I don't know, bake in front of some heat source. We wanted to lay our bodies on hot sand and just let some heat source like the sun bake down on us, right? Well, because our bodies are made up of 70 to 80% water, our bodies have the capacity to sit under a heat source, take in that heat, and our body temperature doesn't change too much, right? So it's very important. We need to keep our body within a very small range. So water having a high heat capacity, we can expose it to a heat source, doesn't change much. The I want to look at here is the units for specific heat capacity. So these units are kind of odd and cumbersome, but when we start working problems, they're going to be very advantageous. So the units for specific heat, the specific heat capacity are joules on top, grams, and degrees Celsius on the bottom. So this is the unit for specific heat. It's not the formula. So that is the units for it, okay? So kind of large, kind of cumbersome, but what we'll see as we start working these problems is they will strategically cancel other units out, which is very helpful. Okay. To an example here. Let's say you find a penny in the snow. I want to know how much heat is absorbed by the penny as it warms from the temperature of the snow, which is 8 degrees Celsius, to the temperature in your hand, which is 37 degrees Celsius. We're going to go ahead and assume that the penny is pure copper, and it has a mass of 3.1 grams. Okay. This problem, we're going to use the following formula. There it is. The formula is Q equals change in temperature times specific heat. Anytime I'm using a formula, I like to take inventory of what I know, try to see what it is that I'm trying to solve for. So over here, I'm just going to take inventory. Q, M, delta T, and specific heat capacity. Okay. Back to this problem, it says how much heat is absorbed. What variable is it asking for? If it doesn't immediately jump off the page, that's okay. We could do process of elimination. But when it says how much heat is absorbed, this is the variable that we're solving for. We're solving for Q. Okay. Warms from a temperature of the snow, which is 8 degrees Celsius, to the temperature of your hand. So we're going to look at this change in temperature piece. Remember, change in anything is always final minus initial. So temperature T with the subscript F is temperature final. T with the subscript I is temperature initial. Okay. So in the change in temperature, what is the final temperature of the penny? After some time has passed, what is the temperature of that penny? Yeah, it warmed up to 37 degrees Celsius. Initial temperature of the penny when we found it in the snow, it was -8 degrees Celsius. So final minus initial, so 37 minus a -8. So our change in temperature that's our change in temperature. This here, we're going to assume that the penny is pure copper. Well, by assuming that it's pure copper, that's going to give us our specific heat. So if the penny is pure copper, we know the specific heat for copper is 0.385. And then remember our units are joules, grams, degrees Celsius. And then lastly, it has a mass of 3.10 grams. Okay. So immediately jump off the paper that heat is what we are solving for. Once you take care of all the other variables in the problem, Q is the only thing that's left. So now that we've tabulated our variables, let's just plug this into our equation and chug through it. So Q equals, mass is 3.10 grams. Temperature is 45 degrees Celsius. And our specific heat is 0.385 joules, grams, degrees Celsius. Where the units for specific heat are going to be very important. So looking at specific heat, I have grams on the bottom of a fraction, And over here I have grams on top, so those units cancel. Specific heat, I have Celsius on the bottom. I have Celsius here in my change in temperature. So what is the only unit that is left in this problem? It is the unit of joules. That's great news because we're solving for Q. And remember, Q is heat or Q is energy. So the units on our Q, our energy, is the joules. Okay. Now we just need to plug this into our calculator and solve. We have 3.10 times 45 times 0.385. And we get that the amount of heat that is being absorbed is 53.7 joules. Okay. This helpful